And as Paul just said, it's an introduction and demonstration of antenna modeling with EZNEC. And I thought I'd start out and just say, why do we want to do modeling? And well, it's probably pretty obvious. We can experiment with designs before you build the antenna. So it's a lot easier to do it on a computer than it is to actually go out and build it and cut and tried and all that kind of stuff. And also partly radios are getting much harder to build by yourself. The modern radios are just so good. There's very few people who homebrew radios, but it's much easier to homebrew an antenna, which is a very important part of your system. So we can see the effects of different parameters on the antenna performance. And the parameters for an antenna are the height, ground type elements, which are their number, size, configuration, its orientation. You can make it horizontal, vertical, sloping, whatever. You can put loads, RLC type anywhere in there, coils and capacitive hats and whatever on your antenna. And you can model transmission lines as well. Okay, so as you change all these antenna parameters, you can see how the performance changes in terms of the azimuth and elevation gain patterns. These are what you see in QST magazine and any other radio magazines. You see that. And sometimes you see the SWR patterns as well. And efficiency is a very important part of your antenna. So this was prompted by the designer of EZNEC is retiring. So he made EZNEC Pro 2 version 6 free. And you can get it at eznec.com. Just go there and download the program. In the past, I've used 4NEC 2, which was another antenna modeling program, and they're very comparable. I think EZNEC is so easy to use. 4NEC 2 has a graphical interface, which kind of makes it easy too, but everybody uses EZNEC, so when it became free, I think it's kind of a no-brainer for us hams to start using it. EZNEC uses the NEC 2D calculating engine. NEC stands for National Electrical Code. The 2 is version 2, and the D is double precision. By the way, if you have a computer that without a lot of memory and or speed and whatever, there is a single precision option under the EZNEC Pro 2 version 6. But I see no reason to use single precision when double is available. And that was developed by the Lawrence Livermore National Lab. So it's a public domain, even though they charge for it. Well, they charge for more advanced versions of NEC that can do fancier things. It runs under Windows, and unfortunately, there are no Macs or Linux versions of this, although there might be other antenna modeling programs available for Mac or Linux, but I haven't looked for them. Before I get started with the demo, I just wanted to say there's a really good introduction, and I'll show you once I open up EZNEC. I go to Help Contents Test Drive, and it'll take you through a tutorial of how to do antenna modeling and how to use EZNEC. And we have to know how to save a file. You do some work and you want to save it. And that's just like any other Windows program. You open a file and you save it. One thing, EZNEC has no blank page. You just can't start up with a blank screen. you have to open a previous antenna model, and then you can change it and save it however you want. I'll go through these steps as I do the demo, but you have to set your frequency, and you can go back and change it real easily. You also have to set your ground type and description, and then you probably want to click View Antenna, just so you can see what your modeling is doing. And then you go to the wires menu and you add, delete, modify wires and do whatever you want. And I'll show you how to do this. And you need at least one source in there. You can have multiple sources and you can control the phase between them, whether they're voltage or current sources, etc. And then you want to probably look at, you set the plot type and click FF plot, which is the far field plotting, to see the gain patterns. And then you can click SWR, and it'll ask you for a range of frequencies, and it'll give you the SWR for that antenna over that range of frequencies. And then you can add loads, transmission lines, and a whole bunch of other stuff that we probably won't get much of a chance to go into here. Some hints. In most cases, the segment size, you have to pick how many segments are in every wire. And it should be around 20 or 40 segments per wavelength. You can do more, but it takes more computation time. And on our modern computers, that's not a problem. For most HF antennas, I typically just use one segment per foot. So on 20 meters, well, here's an example. If you use their guidelines for EZNEC, a quarter wavelength would need 5 to 10 segments. Well, 20 meters, a quarter wavelength is about 16 feet, and I'd put in 16 segments. No problem at all with that. So but that's just a general guideline. 5 to 10 segments per quarter wavelength to get a good model. And one thing I found out using EZNEC, you have to pay attention to the wire diameter. And in fact, in EZNEC, everything is a wire. Even a 5-inch tube is a wire, okay? So you can vary the diameters. You can have tapering elements if you want. It just takes more modeling to specify all that. And here I say EZNEC, tubing, etc. They're all called wires, okay? And in general, careful modeling will give you accurate results, and sloppy modeling will give you poor results. That's pretty much what you would expect here. EZNEC does automatic geometry checking and segment checking. And so once you click far field plot, it'll automatically do these checks and let you know if it found anything that doesn't look right. So you don't have to get too worried about it. You can just try something, and if it doesn't complain, it's probably a pretty good model. The EZNEC does not automatically calculate efficiency. So you have to calculate it yourself. You model your antenna, and there's an average gain of your antenna, and then you remove the losses and calculate the average gain again and just take the ratio, and that's your efficiency. Average gain is shown whenever you do a 3D plot, which I'll show you. And losses, these are the losses in wires, wire insulation, loads, transmission lines, and ground. And obviously this is a no-brainer, a lossless antenna, set all the losses to 0 and model it, and then you get your average gain for a lossless antenna. And the ground losses you set to 0 by selecting a perfect ground. I think that's the end of my, yeah, that's the end of that part. So Let me fire up EZNEC. So you install the program. It's pretty straightforward. And I apologize for the small lettering here. I'll try to explain things as I go through it. But this is the screen that comes up automatically. And if you go up here, in fact, I changed my cursor to this bright, bigger cursor just so you can see where I'm pointing. If you go up here and click Help, Content, you'll get their whole help screen, and here's the test drive. So if you want to go through this yourself, you can go through all these steps on building an antenna. So that's very informative. And there's more about modeling and all that kind of stuff in here that would be very useful for you. So yeah, unfortunately, this doesn't scale up at all. But as I mentioned, well, okay, I'm going to go through and open an antenna that I had here. I'll call this one's called a dipole. So that's the antenna that I just opened up that file, and you can open any file you want. You set the frequency, so you go over here, you see I have it at 14.15, but if I click on that, it lets me change the frequency to anything I want. I can make 14.2 or something like that. I'll just do that right now. And that's changed the frequency, and that's the frequency it's going to use for this model. And it gives the wavelength in feet. I've already selected the units. So here's the units. I have feet, but you could use meters, millimeters, feet, inches, wavelengths. But I'm used to using feet. Now, I'll come back to wires. That's a very important one. But you also, and it has one source, you pick the ground type. And right now I have a real ground, high accuracy real ground. Mini neck is also a very good ground. Or you can pick free space, or you can pick perfect. So when you go to the lossless calculation, you picked a perfect ground here. I'm going to cancel that because I want the real ground. And if you pick a real ground, well, the ground description has different media, and now I have to right-click on this box here, and it brings up all the different types of grounds. I picked an average ground. You can pick an extremely poor ground up to salt water, okay, as your ground. For most of my stuff, I like to use just an average ground for that. So that's how you specify the ground. Okay, here I'll bring up the wires menu. And right now, I started this with just one wire. And what does that wire look like? I go to View Antenna. And this you can rotate by changing your cursor. And for this demonstration, I just started with one little wire that goes from minus 3.2 feet to plus 3.2 feet at 21 feet high. So there's not much to that, but the reason I did that is I want to show you how you add a wire to that. To add a wire, I go to this line with a star in it. I right click and I want to connect to wire 1. So I'll type in a 1 there. And the connect it to end 1. Okay. So it's connected these two ends of the wire together. The other end of the wire I just added goes to ground. What I want to do is make it at the same height. I don't know why I picked 21.2883, but I'll put that in there. 21.2883. That's for Z. So I got the same elevation in both of these. And the Y, I'll just go out to 18 feet. And I'll hit return. And it drew the wire over here. So now I'm going to do the same thing. I'm going to make another wire coming out this side. So I'll right click, connect it to wire 1, but now end 2. And click OK. And it's now gone out the positive way, so I'll make the same elevation, 21.2883. Oh, I made a mistake here already. I'm going to put 18 here. But this one should have been a minus 18. Oops. Backspace. There. This one started at the minus end. Wire 2 started at the minus end of that short little wire 1. It went out in the negative direction. The other wire 3, started at the positive end, went out to 18 feet in that direction. So at this point, I could click Save As, since I've done something, and I'll save it in the same file. I want to replace it, yes. Okay. I've set the plot type to 3-dimensional. I like to use that. And let's do the far field plot. And you immediately get something like this. And you can rotate it any way you want. And then we'll show the 2D parts of that. And right now it's showing the, you can see this red line here. So it's showing the elevation pattern for maximum gain. And this little green point, which I'm pointing at right now, has a gain of 6.72 dBi. You can click anywhere along here, and at 25 degrees elevation is 4.88 dBi. So you can explore this all you want. And one thing I'm going to do right now in the elevation pattern is I'm going to save this trace. And I'll just call it dipole. Okay, that's because I want to compare this antenna to something I do later. Okay, so that's the how you get an elevation pattern. You can also click to azimuth, and it shows an azimuth pattern. It's very quick doing all this stuff, and I could come up here at a higher elevation, go to azimuth, and it'll give me the elevation or the azimuth plot at that elevation. So you can go back and forth and explore all you want. And in fact, you can change the elevation slice right here as well. So just a lot of stuff you can do to visualize the antenna patterns. Okay. One of the things I said for the efficiency calculation, once you do a 3D plot, down here, you'll see the average gain, which is 0.940. And that's the average gain of your antenna for this particular configuration. So, okay, that's 0.920. Let me write that down, 0.920. And I'm going to just do a brief switch this to perfect ground, click OK, and do the far field plot again. And now the average gain is 1.216. So I'll divide my first number by 1.216, and I'll get a gain of about 76%. So that's how you, or excuse me, an efficiency of 76%. So my original antenna with the real ground has about a 76% efficiency. And it's that easy to do. And in fact, if you didn't follow along with what I just said, go to search, type in efficiency. And click on antenna efficiency, double click, and it explains everything I just told you right there. So it's in the help file on how to do that. So, okay, so that's the gain patterns. Now, what about SWR? So this antenna that I have, you can see here a dipole. I'll click SWR, and I've already done this. I'm going to scan from 13 megahertz to 16 megahertz in steps of 0.1. And I'll just type run. And this is what I get. So this antenna has a minimum SWR at 13.2 megahertz. And we'd like to have a minimum somewhere around 14.15 or 14, let's go with 14.2. So the nice thing about EZNEC, it'll do the automatic rescaling for you. So we look at the frequency of the minimum here, 13.2. We come up here, type in a frequency of 13.2, click OK. Had a few little minor errors, but nothing important. And now the frequency is 13.2. Well, we click it again, and now we'll put the 14.2 and then click rescale. And click OK. And it automatically rescaled the antenna. And now if I do an SWR plot, the same one, the minimum is down here, around 14.2. So it adjusted the wire lengths. In fact, over here you can see where I had 18 feet, it's now 19.78. Oops, where I had 18 feet, it's 16.7. So it shortened it in order to raise the minimum SWR point. So that's a really handy feature in EZNEC if you want to get how your antenna can tune over the band. Yeah, in fact, you can click each one of these. There's 13.79. So at 14 megahertz, we have a SWR of 1.49. At 14.35? So we're going for, we're clear down here, 14.4, 14.4, 14.3. We're still down in this, we've got the whole band at a pretty low SWR for this. So if we did this, we would now go out and build our antenna with 16.7 feet, which is, most people would tell you that anyway, for a dipole. So the and the elevation is 19.7 feet or 19.8 feet. So now you can go out and build that antenna, and you'd expect performance pretty close to what you got from EZNEC. All right, let me now modify this dipole and make an inverted V out of it. So to make an inverted V, one of the things you can do is you can put your cursor on any of the wires, and that says wire 2, end 2. Up in the upper right corner of that box, upper left corner of the box, or the upper line of that box says wire 2, end 2. And in fact, it gives you the length of that wire segment and the diameter and all that stuff. So that was wire 2, end 2. So I'm going to come over here. Here's end 2 of wire 2. I'm going to right click, and I'm going to do elevation rotate end, and I'll do by minus 45 degrees. And it just tilted that part down. Kept the same length, everything. I'll do the same over here for this wire 3, end 2. And I'll rotate that down by minus 45 degrees. And there I have an inverted V. You don't have, it does all these calculations for you. You don't have to put in the coordinates at all. You just rotate. By the way, while I'm here, you can connect this end to another wire end. You can change its coordinates, its length by a certain amount, or length to a certain amount, multiply the length by a certain amount, divide by whatever. So there's a lot of wire those are the main things you do by moving your wires around. So now we have the inverted V. Let's do that SWR plot again just to check. And it has a minimum of 14.4. So actually we would probably have to rescale that the way I did before. But I don't think I'm going to. There's 14.1. It's still, yeah, this is a little bit high, which means it's a little bit short. I'm not going to rescale it now because I just wanted to show you some more things here. If we do the far field plot on this, it's here you get the average gain again. You can do the efficiency calculation, which I'm not going to do because we've done enough of that. But let's do the elevation slice like we did before. And show the 2D. So this is the same plot we did for the dipole, but now remember I saved that trace. So now I'm going to add a trace, which is that same dipole that I had. Now the dipole is in blue around here, and my inverted V is this black line here. So now you can see the difference between the inverted V and the dipole. Unfortunately, you can't click on the dipole line to get the actual number, but you can visually see the difference on the elevation pattern here. And you can save a trace for any pattern that you want. I just picked the one that was the maximum elevation pattern. So those are some of the things that we can do easily with that. Oh, one thing I forgot to mention before, when you do these, it gives the current distribution in the antenna, which is, I find, very useful because the maximum radiation occurs for the largest or the largest radiation occurs for the largest currents. So the end of the antenna doesn't radiate very much. So the important parts are the ones that are, in this case, closest to the feed point, to the center of the antenna. So yeah, looking at the currents is very instructive as well in your antenna. I'm going to do one more antenna. I'll change this, okay? I'll save it. This is one, I have a buddy pole, and I use 4 arms instead of 2, and it's a horizontal for 20 meters. Oops. It was asking if I wanted to save this. Cancel. I'll continue to open it. Now I'll open this one. Okay. So here's my buddy pole. I've already modeled it with, you can see the wires. I have that center segment as before, but now these wires 2 and 3 out here, I've picked 0.45 inches in diameter because that's the diameter of the tubing that I'm using. This one has a load on it. Oh, I forgot to show you before. It also has a source. So, yeah, this has a source on wire 1, 50% from the end. So actually you have to really zoom in to see that. So the source, and you can zoom in if you want to see the details. Here's wire 1, a close-up view of it. It has 3 segments. As it says here, 3 segments. And it goes from minus 0.15 to 0.15 feet right here. And then wire 2 is attached to this end, and wire 3 is attached to, what did I do?
It looks like W0PAL tried sharing his screen, so just reshare there, Ron.
Okay, let me find, so that's not what I wanted. Let's see here. That's the EZNEC stuff.
Yeah, just go to the up arrow again, Ron, and it should give you the option to reshare there.
Yeah, I'm trying to find, yeah, there we go. And I'll do the screen. So you all see my screen now?
Yeah, we're back. Thanks, Ron.
Okay. So anyway, this is my buddy pole. I'll zoom back out on that. It has 2, so I showed you the source. It has 2 loads in it. So I click, see, I just want over here, click loads, okay? And it brings up the load screen. And the loads are, you specify load number 1 is on wire 2, 37.5% from end 1. So it's 37.5% out. We get here to this load here. And it's a parallel configuration where R and C are open, and I just have a coil in there of 4.49 microhenries. And coil number 2 is attached to wire 3. That's this one over here. Same distance from the end. And it's 5.16 microhenries. These are the settings I use for, the coil taps for the buddy pole. So anyway, you can add loads like that, transmission lines, transformers, L networks, Y parameter networks, blah, 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 okay? So let me do the SWR on this antenna. Okay, I don't have anything in here. Let's just go from, again, 13 to 16 by steps to 0.1. Click Run. And it gives me a minimum SWR around 14.2. So this buddy pole, in fact, these lengths and coil parameters agree exactly with what I have in the field. And I get a good SWR on that buddy pole. Again, that minimum point's at 14.2. So most of this region is well under a 3-to-1 SWR, and I have a 10-to-1 tuner, so they can handle anything that buddy pole has right there. So yeah, one thing I wanted to show you here. Well, okay, I can do the far field plot, and you come up with this typical thing here. Okay. So yeah, I'll go to the 2D, which is the elevation plot, and I'll save this trace just for fun, and I'll just call it BP. Save. Okay. And what I'm going to do now is take this horizontal configuration and make it vertical. Where am I here? I have trouble rotating 3D things. Okay. So anyway, this is a buddy pole at 16 feet. What I'm going to do again is for wire 2, rotate this by 85 degrees. For some reason, it really doesn't like 90 degrees. But anyway, 85 is close enough for now. I could reposition it later if I wanted to, but oops, I want to make that a minus 85 degrees. Okay, that's going down. This one down here, I'll rotate by plus 85 degrees, like that. So now I have a vertical configuration. This all checks out. The lowest point here is 7 feet off the ground. So that's basically my buddy pole just changed to a vertical configuration. We could do the SWR again very quickly. And it hasn't changed. There's still 14.2, so it still has good SWR. Do the far field plot. But now this looks more like a vertical antenna far field plot. Show the 2D. And let me add that trace of the BP, of the horizontal configuration. And you can see the horizontal configuration has these gains, and that vertical configuration, this. So ever since I saw this, I said, I'm going to always use a horizontal configuration. Because this is at 35 degrees here. I get a gain of minus 2.53. We're out here, we're at about, oh gee. Okay, the outer ring is 5.65, and we're down to minus 5 here. So this is about 4, roughly, okay? And I can go back to the actual horizontal configuration and get that exact number. So antenna modeling here just really helped me define what I want to do with my buddy pole. And I've used it for my backyard antennas and several others. Let's see. So I'm going to just wrap up and No, I don't want to change it. Okay, save it. So I'm just going to go back up. There's a lot of other antennas in here. Let me just pick one, a 4-square with a Z match. So this is one of the ones that comes with EZNEC, is this 4-square antenna. This has fancier loads. These are all phased and they're virtual points, transmission lines and stuff like that. I'm not going to go into the details, but if you just want to look at a far field plot, you can see that it has a fairly good gain up here of 3.35 and very low gain. So it has a pretty good front to back ratio just by adjusting the phase of each of these 4-square on each one of those antennas in the 4-square. So that's one example. Let me show you a, let's see, I think there's a Yagi down here somewhere. Where do I have a 20 meter 5-element Yagi? Yeah, here. So here's a more complicated antenna. You can see a lot of elements in this one. And it's a Yagi antenna. So this takes a lot more patience. Again, we can do the far field plot and get a Yagi pattern. This is in free space. I guess you could add a ground to it. Let's do a real ground. Oh man. Okay, let's not do this. These are all connected to ground, so we'll have to give them all some elevation. Oh, there is a way to raise the antenna. Let me wire. Change height by. So all the wires change the height by, let's put it up at 30 feet. Oh, these are in inches. Okay, 300 inches. Let's do that. So now we can do a far field plot and we get something more like a Yagi pattern out of this. So anyway, there's just a lot of different things you can do. And I guess with that, I'll leave it here and ask if there's any questions about this. I'd be glad to answer them.
If anyone has questions, go ahead and raise your hand and I'll moderate here. Mike, N1XK, go ahead.
Yeah, nice presentation, Ron. Just had a quick thought. What did you see if the difference in the buddy pole results were due to ground losses?
Oh, okay. Yeah, I didn't go through the efficiency on that, but I could have. Let's see, okay, I'm not going to change this one. So I'll open my buddy pole again. And so I could calculate the efficiency of this. Remember, to get the efficiency, you make your plot type 3D. Click this, and now we get 0.742. Okay, let me do a 0.742. And then we change the ground type to perfect. Click OK. Do another far field plot. And now the average gain is 1.014. That gives me an efficiency of 73%. So the 27% were ground losses, is what you could tell from, because all I did was change to a perfect ground with no losses, and then back to my other antenna with losses. So yeah, I could say 20% of my antenna performance is lost in the ground.
Yeah, I guess what I was wondering about is when you rotated the buddy pole to a vertical antenna,
Yeah,
what was the difference there?
I'd have to go through and do that again. I'd be glad to do it.
I'm just curious.
Yeah, I haven't done that, but
Yeah, because you're looking at 20 foot high for the horizontal dipole, and the end of the
yeah.
end of the vertical one was 7 feet in the vertical
Okay.
division, vertical one.
Right. So this is where the current helps you. You see this configuration has high current near the center. And then we get to the coils and then it drops off. Vertically, it would do the same thing. In fact, we could, again, rotate that in by 85. Rotate the other end by minus 85. And now we can do the, well, now it's perfect. Okay. Well, actually, let's go back to the real and do the far field plot. And we see the average gain is 0.189. Let me write that down, 0.189. Now I'll go back and change the ground to perfect and run that plot again. And now the average gain is 0.697. That's 27%. So that means 63% of your losses are in the ground. So yeah, you're quite right there.
Yeah, it's also a high voltage point at the end, so you might be getting some capacitance effects.
Yeah, yeah, it could be. These are the current patterns. I think, well, all right, there's way more to this. We can bring up a screen like this. The different segments, it gives their, this is the current plot, magnitude and phase of every segment that you have. I don't know if, well, the source has the voltage and stuff like that. I'm not sure if I can find the voltage at the end. I've never tried to do that. But you're right. This would be a very high voltage point out at the end.
Yeah,
you can see.
Pretty interesting.
Yeah. Yeah, this has more currents closer to the ground. So that's probably part of the reason that, yeah, more ground losses. Yeah, it's what's fun with this is you can just keep exploring different things. And you learn a lot about antennas by just trying it here. Much easier than building it and putting it out in the field and taking a bunch of data, you know. And I found these models to be pretty accurate within a few feet for big antennas, and within a few inches for like a 20-meter antenna. So usually when I build it, yeah.
So very cool. Thanks.
Yeah. Mm-hmm.
We've got a couple more questions queued up here, Ron. First is Clint, K0GR.
Got a couple questions, Ron. I noticed that comes with some models, some templates that you pulled up. Right. Is there more on the web that, like, is there a repository where people have shared other projects they've ran and you can go tap into those? Do you know of?
Not that I know of, but I bet there are. I like building my own models, so I never look for anybody else's.
Okay. Well,
but there probably are. If you just Google or search for EZNEC models, you'll probably find a bunch of them.
Right. So you showed us how to add a wire to the end of another wire. How do you add a wire that's not connected, as in it's floating? Like if you wanted to build your own Yagi from scratch?
Yeah. Okay. Let's say, for example, I wanted to add a wire here. All mine, I'm keeping X equals 0, but let's say I'll go from Y equals 22, elevation of 20, to X equals 0, Y equals 25, and it'll go to 44. Hit return, and it drew this wire over here.
Oh, good. That's
So
pretty simple.
Yeah. You specify the court. Then you can actually change the length of this wire. Change it to, let's make it 77 feet, okay? And made a much bigger wire. So, yeah, you can do all sorts of stuff.
So could I take that 20 meter Yagi and scale it down to like 70 centimeters?
You probably could.
Okay.
Using that same technique, you find the place where it has a minimum SWR and put that as your frequency, and then change the frequency again with the with this rescale thing checked to the new frequency, and it would just scale the whole thing.
It scales the wire length and the distribution of the wires?
Yeah, it scales everything, all the coordinates, X, Y's, and Z's are all scaled. All the segments, you have the same number of segments, but it does not scale the diameter.
Okay.
You can go back later and change the diameter if you wanted to. So yeah, that scaling is really handy for, you can make a 40 meter antenna out of a 20 meter antenna or vice versa. So.
Great, thank you.
Yeah. Mm-hmm.
All right, up next, we've got Bill, WO0JK, go ahead.
Thank you for the presentation, Ron. I guess I think you mentioned this at the beginning, but I think I missed it. So when you're looking at the material, everything's modeled as a wire, and if you're using, say, copper tubing instead of copper wire, are there some guidelines for what you use for diameters, or how you account for the material?
Okay, yeah. For my buddy pole, I actually measured the diameter of these elements, and that's what I use for that. I probably should have changed. You click on this. The wire loss is for copper. You can click on that. You can pick 0, which is if you really wanted to do a lossless antenna, you would actually pick 0 here. You can pick aluminum, tin, zinc, or you can user define your resistivity and permeability. So, yeah, I could easily just change that to aluminum tubing.
Okay.
And of this diameter that I have for each section here, and go ahead with that. For the Yagi with tapering, now you have to get separate wires stacked end to end and change the diameters. So.
Thank you.
Yeah.
And Skip, go ahead.
Well, thank you, Ron. And in the list of variables in the upper right-hand corner, I see transmission lines and transformers, which I assume are balance or some kind of substitute for that. What are the variables within those categories?
Okay, transmission lines. Here's a transmission line. You'd have to go from, actually, I haven't used transmission lines on EZNEC. But you tell where to connect it to. You tell the length, the Z0 of the line, the velocity factor, and I'm not sure what reverse normal is. And you put in the loss, dBs per 100 feet. And the loss at a certain frequency. So there's a lot of things you can specify about transmission lines. I should probably get around to doing that. Yeah, open. This says short circuit, open circuit on a transmission line. So I haven't had time. It just became free last month, so I haven't had time to explore transmission lines. But there's plenty in here, and also under help, you search for transmission line. And it says about transmission lines here. It'll tell you how to model transmission lines.
Okay.
So, yeah. That's transmission lines. Transformers. Again, you got to put it on a wire, a certain percent from end 1 or end 2. And port 2 connects to another wire, a certain percent from end 1 to end 2. And the relative Z. So yeah, you can give a 1-to-1 transformer. My audio transformers are like 600 ohms to 600 ohms, whatever. Yeah. So yeah, you can enter transformers that way. I ought to try that because I use transformers all the time in my antennas. Haven't gotten around to modeling it yet, though.
Okay. Thank you.
Yeah.
Any other questions for Ron?
Sure, can you hear me?
Yeah, go ahead, Klaus.
Okay, Klaus here. When you model antennas, do you also put into the model other objects, foreign objects, to see how they react to your antenna?
Oh, other objects? Yeah. Yeah. You can build other structures around your antenna. That's the principle of a Yagi. You feed one of the elements and the other elements interact with it to give you the gain pattern. So yes, you can put other structures here. Let's see. I'm trying to see. I know you can add like a wire mesh. I'm trying to find it right now. I haven't done that. I've seen it. You can model a car, for example, if you want to put this next to a car. Mm-hmm. Yeah, and buildings and other things that might be important. So it's possible in here to do all that. And it'll actually model the interactions with any elements you draw on the screen here.
Cool, thanks.
Yeah. Mm-hmm.
I've got a question for you, Ron. I noticed that in both of the antennas that you modeled, both the dipole and the buddy pole, you had a center wire that was, 7 or 8 inches, and then you added your wires to the end there. Is there a reason that you do that versus just connecting the 2 wires to each other with the source maybe in the center?
Yeah, there's not a real good reason. You can actually model a dipole with just one wire.
Right.
Make it, 20 meters, make it 33 feet long, and make sure you have an odd number of segments so you can put a source in the center. Yeah, you can do that. The reason I did that is if I want to rotate one arm and the other. So for the buddy pole, let me zoom in here. Oops, that's zooming out. So I could take this element here, wire 2 N2, and I'll rotate the end by plus 45 degrees. There. Well, I did that on wire 3. Sorry. Oh, because I'd added this other one down here. Okay. Anyway, yeah, you can easily change that without changing your source.
Okay.
It's possible to, and in fact, I've done it. You put 2 wires end to end, and under source up here, put it 0% from one end. And it will actually put the source on both wires, just to make it symmetrical.
Right.
Yeah.
Is there any particular calculation? So I noticed on the one it was 0.6 feet, and here on the buddy pole it's 0.3 feet. Is that something that you scale by band, or is it just a number that you kind of toss out there? I'm just trying to understand, because I've wanted to do more modeling and have not quite been sure where to start. So.
Okay. Yeah. Actually, I started with like 0.01 feet. And the segment check told me that was too small.
Ah, okay.
So I kept increasing it until it didn't complain.
That works.
Yeah. Yeah. So yeah, segment check is real handy. Yeah, it just tells you when it doesn't like stuff. And I can picture in modeling where you can get too small of a segment.
Mm-hmm.
And then you get round off errors and blah, blah, blah. So, yeah. So, yeah, there's no real good reason for that, using that center wire segment. But it's just kind of the way I like to do things.
Sure.
Yeah.
Looks like we've got another question from Clint. Go ahead.
Yeah, I'm curious if you had elements that you kind of were happy with the length, but you were trying to adjust the boom length on a Yagi. Can it solve for one of them? Like, can you scale part of the antenna and not force it to scale at all?
You can move bunches of wires.
So would you have to, is that more of a trial and error to find a good number?
Yeah, let me go back to this Yagi. You can, let's see, I'm trying to find, well, I'll just give a quick demo. You hold down the control key and you can do this. And then, let's see, I'll change the, where's the change the height? I'll change a coordinate. So I'll change the, this to 44. I don't know. I'll pick some number. So it moved something here. Okay, move those elements. So you can do operations on multiple things at a time. I haven't designed Yagis because it's very tedious to get all the right resonances. You just have to keep, in my mind, just keep tweaking it until something works. Yeah, what I do know is you can take sections of wires and do operations on them all at once.
Good, I'll try that.
Yeah. And I'm not sure what all the operations you can do. Yeah, change height. I'm not sure. Well, let's put in here 50. Oh, did that change? Yeah, that changed the height on just those ones that I selected.
Yeah.
So, yeah. Yeah, you don't have to calculate all sorts of new stuff. You can just kind of, select the right wires and then do all these different operations on them. You know, rotate, let's rotate wires, rotate them all. Oh, and on the Z axis, let's pick it on the X axis. Let's rotate that by 40 degrees. And it went through and took that section of Yagi and did something weird to it. Okay, rotated it. So, yeah, you don't have to do all those detailed calculations of how to rotate an antenna. It'll just do it for you. Yeah.
No, thanks, Ron. Any other questions for Ron? All right. Anything else that you've got for us, Ron?
Nope, that's it. Yeah. I didn't have anything more else to say here. There's just a whole bunch of let's see. Open here. Don't want to save that one, but yeah, there's all sorts of other examples here. And yeah, have at it and see what, here's a log period, here's a VHF antenna. Let's see, zoom in. Yeah, Clint was interested in, this is a vertical with a ground plane. That's one of them that's built in. So, yeah, and its frequency is 146. So, yeah. Anyway, there's a lot of examples to go ahead and try.
Fantastic.
And with that, I'm done.
All right. Well, thank you, Ron. Fascinating presentation, and definitely gave me a kickstart, I think, towards doing some modeling. So thanks for putting the presentation together and for sharing it with us.
Yep. Glad to do it.